syndrome we are getting this corresponding to is error pattern. That means here there is a error in the bit. Okay, so corresponding to this error pattern, we have stored the syndrome code.
Okay, sir.
Okay, and then that is stored in a table. So if this error has occurred, that syndrome will be invoked, and then we will like here that y hat this bit position has changed and error has occurred. So then S will be y H transpose. So that is closest to 100. So that is this syndrome. So then corresponding to this, our stored error pattern in the table is this 6 non-zeros, and that will be E. Then our estimated Y would be Y hat plus E. So all are Y hat. That is the error Y, because there is some error has occurred, and instead of Y we have observed Y hat. So therefore, not only it can detect, but it can also correct the error. Actually, this parity bit concept was there before also, and for the device communications, say microcontrollers, and even in among the various devices of computer, initially people used to code it using 7-bit ASCII code, and then plus 1-bit parity. So however, that if we have just 1-bit parity, then we can detect the error, but we cannot correct it. So very early stages, the concept of parity bit were used. Not only for communication between various devices. Using single bit parity. Single bit odd even parity, that is even number of ones in the data plus parity is even parity, and odd number of ones in the data plus parity is odd parity. So for a single bit, of course, this is the general definition for 1-bit, 2-bit parity, but the people used to have But for a single bit, that means that for odd number of parity in the data bit, that gives even parity, and even number of parity in the data bits gives even parity. So then that parity bit is added to the data and transmitted. Afterwards, Hamming, of course, make it theoretically sound and multi-bit parity concept, and then error correction capability has also enhanced, because this single parity bit code does not have error correction capability. But this is very simple to implement. So that's why for a low budget equipments, this can be used profitably. Like say we have a data 100110, another data 011010, another 100010. Okay, like this, for example. Now, if I here there are 3 ones. So if I consider the parity bit, then if I put a 1, that will be, of course, even parity. And here also same thing. Here this is odd parity. Again, this is even parity. So this is the parity bit, and then this can be given like while transmitting D1 and 1, that will be transmitted together. So data bits followed by the parity bit. So for ASCII code, of course, this I have given 6, but ASCII codes are 7 bits. Now, this concept was little bit modified by making what is known as 2D parity. In the 2D parity, the parity checked for column wise as well. So here there are even number of 0 is even, so even number of 1s, so 0, odd parity. This is also odd parity. This is even parity. Odd parity, even parity, even parity. So this is say that one which we call row parity. So they should be like column parity. Now we can also code this such that the error in the parity bits, row parity bits, can also be coded.
Excuse me, sir.
Yes.
So can you please explain the column parity bit?
Parity. So parity is basically whether it is even or odd number of ones. That is the definition of the parity bit. Okay. So parity even means it is the data plus this unit is having even number of ones. All right. Similarly, parity number of odd means data plus this one is having odd number of ones. Okay.
So, sir, in case of D3, the row parity, we're calling it like odd parity, right?
Yes, yes. Odd number of ones, I think I have written wrongly. 1, 2, 3, 4. So odd number of ones, data plus parity is odd. So that is not true. I think even number of ones in the data plus parity is even parity. And even number of odd number of, no, I think this is wrong written. I think even number of ones in the data, just let us write it, is odd parity, because we are representing the odd parity by a 0 bit. So therefore that is the parity bit is represented. Because for this is the concept of 2D parity, two-dimensional parity. So in the two-dimensional parity, we have row parity, and then we have column parity, and the row parity bits are again coded with a parity bit here. So odd or even. So then this will be transmitted like as a frame. So D1 and then 1 and D2 1, D3 0, data bit parity bit, data bit parity bit, and then D4 1 and then CP and 1. Usually for such kind of communications earlier days, there used to be a stop bit as well to use the termination point of the data. So however, as you can see that here we can detect the error. So any transitions here, any one transition will change, but we cannot detect two transitions. Cannot detect two transitions. Row parity or column parity. Row parity can detect only one error in that row. But cannot correct it. Because suppose there is one error, okay, so therefore parity is not matching. There has to be odd number of ones here. But if there is one transition, either this one is become 0 or this one is become 0, this becomes even. So therefore this parity is not matching. So therefore it can be taken as not matching. So that can also be done by simply XORing it. If you XOR this, this will make it 0. So any one transitions will make it 1, okay, with the parity bit.
Excuse me, sir. So here, even if there are like any odd number of errors, then also we would be able to point out that there's an error, right?
Yes, yes. I mean, if there are 2 transitions, then we won't be able to, uh, like here is 0, here is 0, we won't be able to say that whether there is any error or not. By observing the XOR output of the bit stream, so that can be easily deciphered that there is some error. But in which position the error is, that is not possible to tell. Now, using 2 dimension, again what will happen, that because suppose here it has error has occurred, so then there will be, say, this bit, if it is error has occurred, this one will be affected and this one will be affected. So we will be locate. So 2D parity bit parity bits can locate the error. Therefore can be corrected. So that is possible. So like here, if it is error, then these 2 bits will be changed. But suppose that here there is one error, okay, single bit error. So that will be located. But suppose I have error here also and here also, then same 2 bits will pick up, will not pick up. So therefore, single bit errors can be picked up and also can be corrected by the 2D parity, but multiple bit errors cannot be corrected. So those are the disadvantages that I mean in the Hamming code, and also there are many other codes, but Hamming actually was the pioneer in having this concept of code design and error code design, and also for correcting steps. But there are many such codes are available, error correcting codes. So we don't have that much time to discuss all those, just the basic concepts only we are discussing. But just one thing maybe.
Sir, per data, we cannot correct more than one error, right? If there are 2 errors, it can't.
Yes, more than one error here we cannot correct, but the concept that we have presented before, here we are able to correct actually, because it will invoke various syndrome patterns. Okay, so here also reliably we can correct only one error. In this particular case, we can correct only one error. but there are codes which can correct, which can detect multiple bit error as well as can correct multiple bit positions errors. That is also possible. However, just how that code, this code, our example code, these parity bits are generated. So these parity bits, you can say these are the message bits. Ultimately, your code is generated G into M. Okay. So that G into M, G into M means there will be message bits M0, M1, M2, M3. Say 7-4 Hamming code. As we have discussed before, that there are certain rules that need to be followed for generating these parity bits. So these rules mainly say that there should not be, for like 7-4, we will be using 3 bits, 3 parity bits. Okay, now earlier we have presented that how these codes were generated, that is this way. These are the B0, B1 and M. Finally, B is B0 to Bn minus k minus 1. M was M0, M1, Mk minus 1. And X is the code. So B is equal to MP. So P is the parity bit. Those are given in that matrix. So therefore, we have to now see that how this will be done.
Sir, but there are 12 parity bits, right? Because P is a 4 by 3 matrix.
Yes.
But sir, you have written here that it uses 3 parity.
4 by 3 matrix. Where 4 by 3 matrix?
Sir, the P matrix, it is K cross N minus K.
K cross N minus K. Yes. It is 4 by 3 matrix.
So,
Four
sir,
row.
like all these PIJs, they are the parity bits, right?
Yes, yes.
So, sir, there will be then 4 into 3, 12 parity bits.
Yeah. No. This is 4 into 3. So there would be B0, B equal to M into P. Yeah.
So there will be 3 BIs, B0, B1 and B2.
3 BIs. Yes, there will be 3 BIs. Yeah, you are correct. There will be 3 BIs. No, I wanted to say that this message, there are 4 messages used to generate this B. Okay. So how it is done? Like, where is our code? This is the P and this is M. So it could be done like we can take if we take the first one, suppose B0, B0, that is picking up the first message M0. No, yeah, M into P. Okay, so it will pick M0, M0, M2, and M3. Yeah. M is here, so M0, M2, M3. B0 is M0 plus M2 plus M3. Similarly, B1 will pick up M0, M1, M2. And V2 will pick up M1 plus M2 plus M3. You can see that no two of these formations are using same messages, such that any error in the messages will pick up at least 2 bits, two parity bits. So that means an error in M2 will pick up B0 and B1. Error in M0 will also pick up B0 and B1. Error in M3 will pick up B0 and B2. Okay. So therefore, if we take, so this will give zero, 1, 1, that same matrix we will get 1, 0, 0. And of course, this side is the message only. Now, if we interpret intersection wise, actually we shall see that
So the last entry of the first for the parity matrix is I think 1.
this one. Yes,
Row 4,
yes,
column 3.
yes, 1. Yes, thank you. So therefore, if we put the bits here, M0, so also we should fix one of them. Let us fix this one is B0. Then B0 is M0, M2, M3. So B2 is M3. So this, if I put B2 here, this would be M3. And then this would be M2. Then B2 is M1 here. And this is matching, I think. Yes, it is all right. M0, M1, M2. So that way, any bit transition we'll set two parity bits. But then how do we checking the parity bits? We are checking the consistency by adding them, okay, and or XORing them, because binary addition, 2's complement addition is nothing but XORing. So we are XORing them. So if it is not matching and only in one, then if only one parity bit is not matched, that means what? Because any one bit transition in the message will give rise to transition of a change of 2 bit parity bits. But if there is only one parity bit is not matching, okay. If it is not matching, then that means what? Then it is concluded that the error is occurred in the parity bit. The generation of parity bits can be also interpreted in terms of eigenfunctions, binary eigenfunctions of eigennumbers. Eigennumbers are like those like axes. I mean, or we can simply tell them axis. I mean, axis is one of the eigenvalues or eigenvectors where it can give the direction, principal direction. So for example, if we have 3 bits here, B0, B1, B2, so the eigenvalues should be like their eigenaxis would be naturally 0, 0, 1, 0, 1, 0, and 1, 0, 0. So like in the 3 dimensions, three X, Y, Z axis. So like that also Hamming codes can be designed. So that is another concept that is being used for designing Hamming codes. But I think we will not go into such kind of details. Just for example, we have taken this. Our next discussion would be another code, because code design is not a trivial task in Hamming codes. So therefore, there are many linear code design has come into practice. One popular of them is known as cyclic code. So cyclic code is also a linear code, but apart from is linear code, it is also cyclic. So that means if I give a circular shift, it will generate the same, it will generate a valid cyclic code. Linear code, how the linear code basic property to be checked, that any summation of 2 linear code, any combination of 2 linear code will give rise to another linear code. So from the code book, if we take any two codes and add them, it will generate another linear code. So that's why that is a linear block code. So similarly, a cyclic code a binary code is cyclic code is very popular. Actually, from this concept only cyclic redundant, those CRC codes have been formed. So we should discuss a little bit. We will not go into detail, just the basic concept only we will discuss. A binary code is said to be cyclic. Code if it exhibits two fundamental properties. One is linearity. That means the sum of two code words is also a code word, also a valid code word. Then number two is the cyclic property. The cyclic property is any cyclic shift of a code word is also a code word, also a valid code word. So what is cyclic shift? So cyclic shift is like that. Suppose I have a valid code word x0, x1 up to xn minus 1. So this after cyclic shift of 1 towards the right cyclic shift if I give, or left cyclic shift, sorry, left cyclic shift. Similarly, xn minus 1, x0 and all those things up to xn minus 2. Are the cyclic shifted versions. So they will cyclic codes means that these are also the set of the code word. The code word is represented in cyclic code in polynomial form. So that means x is a polynomial, suppose d, that is equal to x0 plus x1d. D can be like a delay operator. Okay. So therefore, because in the discrete case we have seen, I think you have, those who have studied signal system, they know that there is something called jet transform. Okay. Now it is an equivalent like jet transform, but here we are using D. D stands for delay. So x0, x1d plus, like that. The n minus 1th term is xn minus 1, d to the power n minus 1. So similar to the linear block code, here also we have generator polynomial. Generator polynomial in comma k cyclic code is specified by the complete set of code word polynomials of degree n minus 1. GD is of degree n minus k. Minimum is of degree, minimum degree n minus k. The degree of GD is equal to the number of parity bits. Parity bits in the code. So GD can be written as 1 plus equal to 1 to n minus k minus 1 gi d to the power I plus d n minus k, like d to the power n minus k. So GI, because we are having here binary polynomial, GI is either 0 or 1. So XD, the code word, is equal to AD GD modulo d to the power n minus 1. So that means if it has go to higher degree, it has to be remapped to the original domain. Where AD is a polynomial of D. AD equal to A0 plus A1D, like that, plus AK minus 1 d to the power k minus 1. Given GD, and the message M0 M1 up to k minus 1, just like before we have k number of message bits. Code word is like we have B0, B1 up to Bn minus k minus 1, and then the message bits M0, M1 up to Mk minus 1. These are the n minus k parity bits, and this is k message bits. So if the message polynomial, let the message polynomial be written in D, so just like before we have, this is M0 plus M1D plus Mk minus 1 d to the power k minus 1. So if we multiply by d to the power n minus k, we will have d to the power n minus k md equal to m0 d to the power n minus k plus m1 d to the power n minus k minus 1 plus mk minus 1 d to the power n minus 1. So this can be written as, d to the power n minus k md divided by gd is equal to AD plus BD by GD, because AD plus XD we have taken as ADGD. And XD is equal to this polynomial. So d to the power n minus k md is equal to ADGD plus BD. Now in modulo 2 arithmetic, BD equal to minus BD. So therefore BD plus d to the power n minus k md is equal to ADGD GD. Now therefore XD equal to BD plus d to the power n minus k md. So the steps should be multiply the message polynomial md by d to the power, multiply md by d to the power n minus k, divide d to the power n minus k md by the generator by gd, generator polynomial, and obtain the remainder. Remainder BD. Add BD to d to the power n minus k md obtaining the code word XD. So these are the 3 steps. We have to take some example to explain it. Now, just like before, we have parity check polynomial. That is HG transpose equal to 0. So then we have a polynomial of HD, that is H, GD is multiplication d to the power n minus 1 equal to 0. HD, XD d to the power n minus 1 also will be equal to 0. So therefore, GD and HD are factors of the polynomial one plus d to the power n. That is GDHD or sorry, HDGD. Equal to 1 plus. I shall explain. We shall take one example next day and go it further. Otherwise, yes, it is becoming little problem. So thank you. We shall discuss next day with an example. Now,